NASA has just selected 41 technologies that could shape the next era of exploration at the Moon and Mars. The list is not a collection of futuristic props. It is a practical map of the problems that stand between a spacecraft leaving Earth and a human crew living safely on another world. The most important question is no longer whether we can reach the Moon. We already have. The harder question is whether we can build an entire working ecosystem away from Earth, where every kilogram matters, every repair is difficult, and a delay in communication can turn a small mistake into a crisis. In this episode, we will explore the technologies NASA is advancing, why they matter, and what they reveal about the hidden architecture of a multiplanetary civilization. The story is about rockets, but it is also about dust, heat, water, power, robots, medicine, and the ability to manufacture what explorers need on site. Imagine standing beside a lunar lander during the long night. The sun has disappeared below the horizon, temperatures are plunging, and darkness will last for roughly 2 weeks. A mission that depends only on sunlight cannot simply wait this out. It needs energy storage, highly reliable electronics, thermal protection, and autonomous systems that can keep working while Earth is on the other side of the conversation. This is why lunar power is one of the central themes of the new technology portfolio. Engineers are studying advanced solar systems, fission surface power, and ways to distribute energy across rough terrain. At the Moon's poles, sunlight may reach certain high ridges for much of the year, while nearby craters remain in permanent shadow. Connecting these places could make the difference between a temporary visit and a sustainable base. Power also changes the meaning of local resources. In a permanently shadowed crater, temperatures can remain cold enough for water ice to survive. But ice is useful only if a machine can find it, extract it, purify it, and turn it into something valuable. Water can support life, provide radiation shielding, and, after electrolysis, become oxygen and hydrogen propellant. That chain is known as in situ resource utilization, or ISRU. The phrase sounds technical, but the idea is simple: do not carry everything from Earth. Use the soil, ice, atmosphere, and sunlight of another world to reduce the burden of launch. The challenge is that lunar soil is not soft sand. It is sharp, abrasive, electrostatically charged dust that can damage seals, clog mechanisms, and cling to spacesuits. Future excavators will have to work in an environment unlike any construction site on Earth. They must move through vacuum, tolerate extreme temperature swings, and operate with little or no direct human control. Some concepts use specialized scoops, rotating drums, or thermal techniques to release volatiles from the ground. Every design is an experiment in turning hostile material into infrastructure. Dust is not only a mechanical problem. It can become a health problem. Apollo astronauts reported that lunar dust entered their cabin and irritated their eyes and airways. Longer missions will require improved suit ports, filtration, cleaning systems, and materials that resist contamination. A lunar habitat may need an airlock that keeps the outside environment outside, even after dozens of people and machines have passed through it. Robotics will be the first workforce. Before astronauts build a landing pad, lay cables, or prepare a habitat, robotic scouts may map the terrain, test the soil, and identify stable routes. Autonomous navigation is essential because the Moon has cliffs, craters, shadows, and lighting conditions that can confuse ordinary cameras. A robot working far from Earth cannot wait for an operator to approve every wheel movement. Communication with the Moon has a delay, and a rover may enter a region where signals are blocked. Advanced autonomy allows machines to recognize hazards, recover from uncertainty, and coordinate with one another. On Mars, where one-way communication can take many minutes, this independence becomes even more important. The technology list also points toward a new kind of astronautics, shared work between people and machines. Robots can perform repetitive, dangerous, or dusty tasks. Humans can handle judgment, improvisation, and scientific interpretation. The best exploration system will not be purely robotic or purely human. It will be a partnership designed around the strengths of both. Mars adds another layer of difficulty. Its atmosphere is mostly carbon dioxide, the air pressure is extremely low, and the planet receives weaker sunlight than Earth. A crewed Mars mission would need reliable power, closed-loop life support, radiation protection, and a way to produce return propellant before the astronauts even arrive. Life support technology may be the least glamorous part of space exploration, but it is among the most important. On Earth, air and water seem abundant because ecosystems constantly recycle them. In a spacecraft, carbon dioxide must be removed, oxygen must be replenished, humidity must be controlled, and water must be recovered from breath, sweat, and wastewater. The closer a mission moves toward Mars, the more recycling matters. Resupply is not a realistic safety net across interplanetary distances. A future habitat must behave more like a miniature ecological machine, turning waste streams back into useful resources. Even small improvements in recovery efficiency can reduce launch mass and increase crew safety. Food production is part of the same puzzle. Plants can provide fresh nutrition, psychological comfort, and a biological way to help manage carbon dioxide and oxygen. But plants need water, light, nutrients, and carefully controlled conditions. Growing food in lunar or Martian soil is not as simple as planting a seed. The material may contain toxic compounds, and the environment outside the habitat is deadly. NASA is also advancing technologies that make landing safer. A spacecraft arriving at Mars enters the atmosphere at enormous speed, but the air is too thin to slow a heavy vehicle easily. Heat shields, supersonic parachutes, precision navigation, and powered descent must work together during a short, violent sequence. For human missions, landing accuracy will be crucial because crews cannot afford to touch down far from supplies, power systems, or prepared shelters. At the Moon, the problem is different. There is almost no atmosphere to help with braking, and the terrain near useful polar sites may be steep and uneven. Precision landing systems will need to recognize hazards in real time and divert toward safer ground. A few meters can separate a stable landing zone from a slope that traps a vehicle. Once people are on the surface, radiation becomes a constant threat. Earth is protected by a thick atmosphere and a global magnetic field. The Moon and Mars offer much less shielding. Solar storms can send dangerous particles toward a habitat with little warning, while galactic cosmic rays create a background risk that accumulates over time. Protection may come from architecture as much as from advanced materials. Habitats could be covered with layers of regolith, placed inside natural lava tubes, or surrounded by water tanks and supplies. The most elegant radiation shield may be something already lying on the ground, transformed by robots into a protective roof. Medical autonomy will also become more valuable. A crew traveling to Mars cannot count on rapid evacuation or a real-time doctor on Earth. Astronauts may need diagnostic tools, compact laboratories, robotic assistants, and decision support systems that work with limited supplies. The goal is not to replace medical expertise, but to place more of it inside the spacecraft. Manufacturing is another hidden breakthrough. If a habitat can print replacement parts, repair tools, or structural components from local material, it becomes less dependent on shipments from Earth. Additive manufacturing in microgravity and on planetary surfaces could allow crews to design solutions for problems that nobody predicted before launch. The idea extends beyond emergency repair. Construction robots might assemble antennas, roads, landing pads, and protective walls. Specialized machines could process metals, glass, ceramics, or oxygen from lunar materials. Over time, a base would become not just a destination, but a factory capable of expanding itself. This is the deeper meaning of selecting dozens of technologies at once. No single invention creates a permanent human presence in space. A settlement emerges when many modest systems work together: power that lasts through the night, machines that survive dust, habitats that recycle air, navigation that avoids hazards, communications that do not collapse, and logistics that connect all of it. It is tempting to imagine exploration as a straight line from a launch pad to a flag on another world. In reality, it is a web. A rover depends on power. Power depends on construction. Construction depends on materials. Materials depend on mining. Mining depends on autonomy. Autonomy depends on sensors and communications. Every breakthrough strengthens several other parts of the system. The moon is therefore more than a nearby destination. It is a proving ground. Engineers can test hardware only a few days away, learn how it behaves in vacuum and dust, and improve designs before sending people across the Gulf to Mars. The lessons will not be perfect, because the worlds are different, but they will be invaluable. And there is a cultural shift hidden inside this engineering effort. Space exploration is moving from the age of isolated missions toward the age of continuity. Instead of asking how to survive for a few days, we are learning how to maintain capability for months, years, and eventually generations. The 41 technologies are not a guarantee that the future will be easy. They are evidence that the hard parts are being named. When a challenge receives a sensor, a test article, a prototype, or a field demonstration, it becomes something engineers can measure and improve. One day, a crew may look back at Earth from the lunar surface while a fleet of machines works below them. A power system will be gathering energy, a processor will be planning routes, a recycler will be closing the loop on water, and a shelter will be using the ground itself as protection. None of these moments will look as dramatic as liftoff, but together they will make liftoff meaningful. The future of exploration will not be built by one spectacular machine. It will be built by dependable systems that quietly turn an alien landscape into a place where human curiosity can continue. The moon may be the first workshop, Mars the next frontier, and this portfolio of technologies the blueprint for getting from arrival to endurance. If this story changed the way you see space exploration, subscribe to The Quiet Cosmos for more calm, cinematic science documentaries. The universe is vast, but the path outward begins with solving one difficult problem at a time.